Welcome back. Chapter 7, Part 2. We're continuing our discussion about continuous probability distribution, but this time we're just going to go through specifically the examples that come at the end of the chapter. Which chapter? Oh, Chapter 7 out of this textbook. If you're familiar with any of these series of videos, then you'll know that I'm talking about basic statistics for business and economics by these folks right here, Lynn Marshall and Wathan. I don't know them. I don't know if I'm pronouncing their names right, but those are the authors, and you always got to give props where props is due. If you've seen these slides before, it's because you've seen them out of that textbook. If you don't have these slides, you don't have that textbook, hopefully we'll be able to give you some information that's useful. Let's get on to the examples. These are the tips that we described, or these are the things that we need to know out of this chapter. In the first part of the chapter 7 set, we talked about theoretically how all these things come into play. Now we're going to do it practically. We're going to do the application. No examples. Let's get to it. Here's the first one that we discussed last time. It says if we have a mean of $1,000 and a standard deviation of $100, that we've got this particular standard normal distribution here. Now our question is, what's the likelihood of selecting at random someone from this distribution who has a weekly income of between $1,000 and $1,100? So the first thing we do is we take the raw score and we convert it to a z-score. No, that's not true. The first thing we do is draw the picture. Draw the picture, write the process. Or write the process, draw the picture, whatever you want to do. Raw score gets you to a z-score, gets you to an area, gets you to a proportion or probability. That's the first thing. And the second thing is to draw your curve, whatever it is. It doesn't have to be artistic, it doesn't have to be perfect. It can be a triangle for all I care. As long as you've got that peak shape with a line in the middle indicating the mean, give yourself an x-axis and label what you can. So we take our raw scores of 1,000, convert it to a z of 0. Should be easy, it's the mean. Take the raw score of 1,100, convert it to a z, that's 1. So we take raw score, convert it to z-score. Then, in order to get from z to area, which is the second step of the process, we have to go to the tables. So we go and find the z-score of 1 here, and it's the distance between the area is always the distance between the mean and whatever z-score you select. We know that 1,000 is the mean, so we can just look up 1 here, and that's the area, 0.3413. That's the area between the mean and 1. Area goes to probability or proportion. In this case, the proportion is 34.13%, which also happens to be the probability. If you want to put the decimal between 0 and 1, 0.3413. The point is that area, 0.3413, is the probability that selected at random you will find one of these foremen making between $1,000 and $1,100. It's the same example we used for part A. It's the most basic example because it's exactly how your textbook table is used. There's no arithmetic other than finding the distance between the mean, z of 0, and whatever z-score you convert your raw scores to. That's the first example. The second example is a little bit different. It says, what's the probability of selecting a shift foreman in the glass industry whose income is between $790 and $1,000? First step, write the process, draw the picture. We didn't write the process, but we certainly drew the picture down here. Process goes from the raw score to the z-score to the area, and the area to the probability. In this case, our raw scores are 790 and 1,000. We convert 790 to a z-score. We convert 1,000 to a z-score. That's pretty simple right here. This 1,000, of course, we know is the mean, and by now this arithmetic should be pretty straightforward. Notice that the z has a negative sign in front of it. Z-scores are signed values. Pluses and minuses are so important. We draw that guy down here. We put 790 on the curve, which we know is less than 1,000. We convert it to a z-score of negative 2.1. Then we have to go to the tables and find negative 2.1 in there. Negative 2.1, well, we don't have a negative. Lucky for us, it's symmetrical. So we can find the area on the right side of the curve, clearly, and then just say, oh, that's the same thing on the other side. The area doesn't become negative. The proportion doesn't become negative. The z-score just tells us the direction, above or below the mean. But the area between the mean and the z-score of negative 2.1 is right here, 0.4821. Notice that's the number of this down there, 0.4821. So if we wanted to answer that question between $790 and $1,000, that would be this area right here, or 48.21%. We could also use an Excel function here to calculate differences if you were interested in using that. In other words, we took our raw scores, 790 and 1,000, converted them to z-scores. We used those z-scores to find an area, and that area we used to determine the probability that we select someone between 790 and 1,000. The third example says, what's the probability that someone makes less than $790? First step, write the process, raw to z to area to prob, and draw the picture. We've drawn the picture down here. Picture looks quite similar to the last one. We put 0 down here. We know that's our mean of 1,000. We know we're going to be looking at 790, so we're going to put 790 on this table down here. We convert 790 to a z-score. That's the second thing. Convert the raw score 790 to a z-score of negative 2.1. We go to the table and we see that again that area is the same. The area 0.4821, but I want to know less than 790. Not the area between the mean, but less than. If the entire area under the curve is 1, and half of it, or 0.5, is on the other side of the mean, I know that what I have on this side of the mean to the left is 0.5. If I subtract this area right here, 0.4821, I'm left with 0.0179, or a 1.79% chance that if I select a person at random, that person makes less than $790 a week. I went from the raw score 790 to the z-score of negative 2.1 to the area of 0.4821, subtract it from 0.5, and then I get my probability. Example number 4. Still working with the same data set. The mean is still 1,000. The standard deviation is still 100. In this case, I want to find what's the probability of selecting someone who makes between $840 and $1,200. The first thing I notice about this range is that it doesn't bookend at the mean. It doesn't go to 1,000 or start at 1,000. It's not a tail. It's not less than a certain number or greater than a certain number. And lastly, 840 is less than the mean and 1,200 is greater than the mean. So I'm probably going to have a couple of areas that I need to add up, but let's not get ahead of myself. Raw score to z-score to area to probability. Draw your picture. I draw my picture down here. I know that 1,000 is the mean. I know I want to get from 840 to 1,200, so I draw those things on there. That's all step 1. That's just drawing my picture and putting my raw values on there. Second is I got to turn those raw values into z-scores using the z-score formula up here. This raw score of 840 is a z of negative 1.6. The raw score of 1,200 is a z of 2.0. Third, we take those z-scores and convert them to areas. The z-score here is going to the table and looking up 2.0. When I look up 2.00 in my table, in my z-table, I get an area of 0.4772. If I look up negative 1.6 in my z-table, I won't find it because it's only positive numbers. Lucky for me, it's symmetrical. I'm just going to look up 1.6. I look up this 1.6 in the table and I find an area of 0.4452. Hey, 0.4452, 0.4772. That's what happens when you look up those two numbers in the z table. So I took the raw score and converted them to z, negative 1.6 and positive 2. I took those z scores and looked up what their areas are in the body of the table. Remember, on the outside of the table is the z-score. On the inside of the table is the areas, are the areas. Just like under the curve inside here, those are areas. Inside here is areas. On the outside is z-scores. Don't try to make these inside one z-scores. Don't try to make these outside one areas. That's the thing that some people try to do sometimes is they say I'm looking up some number and they'll try to look up the wrong one. Z-scores are on the outside, areas are in the middle. When you're going to use your z-score to find an area, find your z-score and you see the area. If you're working in the other direction from the probability to the raw score, you have to start with your area and find out what z-score is appropriate to that. Back to this problem, raw score of 840 turns into a z-score of negative 1.6, turns into an area of 0.4452. On the right side, a raw score of 1200 turns into a z-score of 2, turns into an area of 0.4772. You add those two areas to get your probability. 0.4452 plus 0.4772. When you add those two things together, you get 9224. I believe, if I do the math in my head real quick, and that sounds about right. If it's not, it's within rounding. We call it decimal dust. In this case, the total probability is the entire area between 840 and $1,200, or between z of negative 1.6 and positive 2. Do not, under any circumstances, say that that distance is 3.6 standard deviations, which it is, 1.6 on the left and 2 on the right, and say, well, if that's 3.6 in terms of its z distance, I'll just look up that number in my z values, and once I find 3.6 in here, the area will tell me the area. No, it doesn't work like that, because 3.6 standard deviations close to the mean, 1.8 on each side, let's say if it's symmetrical, that's a big chunk. That's, somewhere around 90, 80, 90% of the data. But if you move that 3.6 to one side or the other, I could just slide it all the way over there. So it's on the asymptotic tail. I could have a distance of 3.6 that captures no area. The location of these z-scores is very critical. That's why you got to follow this process. Example 5 here. Same thing, $1,000 mean, $100 SD. We're talking about finding an area between 1150 and 1250. Again, I know I'm looking at a range, but what do I notice this time? Not only is one of the bounds not the mean, but that they are both on the same side. When they're both on the same side, I run into a little bit of trouble. But let's see what happens. The first step, write the process, draw the picture. Well, there's our picture, the process. Raw to z to area to probability. Area. I want to say area. Area. In this case, we draw the picture. The mean is 1,000. We know that. We got to put the mean on there so that we know which side both of these go on. It doesn't matter if you put it exactly where it's supposed to go when you put your drawing on there. It's all about relative position. Is it greater than the mean? Is it less than the mean? Is the other one greater than the mean? Is it less than the mean? Is it greater than the other one? Well, 1250 is greater than 1150 is greater than 1,000. That's why these positions, the relative position, is the important part. Whether or not you draw the picture with any sort of precision, I couldn't care less. In this case, we convert those raw scores to z-scores. 1150 becomes a z of 150, 1.5. A raw score of 1250 converts to a z-score of 2.5. I've taken my raw scores, converted it to a z-score. Now I got to use those z-scores to find some areas. Here we find, oh, that guy's shifted a little bit down there. That's a bummer. The highlights are shifted down there. So don't look at where they're highlighted. It should be up 1 on both of those. That's a bummer. Well, luckily, our picture here tells us what we want. The area between 0 and 1.5 for z is 0.4332. Don't let these guys distract you. 1.50 is 0.332. 0.4332. That's the thing we want. And the z-score, 2.5, 0. We're using that 2.50 column. If it was 2.51, I would look here. But it's 2.50, so it's this one. The area is 0.4938. So now I've got two areas. I've got 0.4938, gets me all the way out here, and 4332, which gets me right here. The area in between them is what I'm after. The area in between them is the difference. What area am I looking for? 0.4938 minus 0.4332 leaves me with 0.0606. In other words, there's a 6.06% chance that if selected at random, the foreman I pick makes between 1150 and 1250 per week. That's going from a raw score to a z-score to an area to a probability. But let's say we go backwards now. We're going to take a proportion or a probability, convert it to an area, convert it to a z-score, and convert it to a raw score. That's the example right here. So this tire company wants to set a minimum mileage guarantee on its new tire. Tests reveal that on average, it lasts 67,900 miles with a standard deviation of 2,050 miles. Also, that the distribution is approximately normal. That's pretty essential. We need a normal distribution to convert to z-scores. What this company wants to do is set the minimum mileage guarantee so that no more than 4% of tires will have to be replaced. So here's the idea, is that I'm going to replace some of my tires, and I want the people who buy my tires to know that if they get a bad tire, I'll replace it for free. I can't replace all the tires. Customers would love that. If I replaced all tires, customers would really love that. I can't replace all. I can't replace most. What I can do is I can replace some tires that fail prematurely. In other words, if half of these last at least 67,900 miles, I couldn't set the warranty there. I could probably set it maybe a little bit below that or a lot below that, but ultimately I only ever want to replace 4% of my tires. So what I do is I start write the process. In this case, it's raw to z to area to probability backwards and draw the picture. Here's the picture. In this case, we're going this way. We need to set the minimum guaranteed mileage so that no 4% will be replaced. We put that marker there and say if the tire does not last that long, we're going to replace. Every tire over here, those tires that only last 30,000 miles or 35 or 50 or 55,000 miles, whatever, these ones are the ones that we're going to replace. But we need that area, whatever that cutoff mileage is, that area can't be more than 4%. This is how you draw the picture. So we put 4% in this tail. Doesn't matter if that's more or less than 4% visually. The fact is we've declared it. We've put an arrow. Also, we know that half are below the mean, half are above the mean. Therefore, 0.5 minus this 4% tells me that this area, whenever I'm talking area, I'm talking about the body between the mean and the cutoff. That's the area. So starting with the probability or proportion, I determine this area. This is the area we need to find in the body of the z table. We also have this given data from the problem, the mean and the standard deviation, so I can put the mean on here. I've got my picture, I've got my probability, I've got my area. Now I need to find that area, 0.4600, in the z table. Well, I can't find it exactly, but I can find something close. 0.4599 is super close to 0.4600. the corresponding z-score for that, I start by going to the left here and find that 1.75, 1.7 and then 5 on the hundredths, that's the z-score that would give me an area of 0.4600. 599, but it's close. That's the z-score that I now have to put into this equation. Wow, look at that, PowerPoint, zing. Negative 1.75. Oh, shucks. Remember when you draw it, you have to put the sign on it. You have to remember that it's a signed distance. That's the whole point of drawing the picture. So you know whether it's going to be negative or it's going to be positive. But now we've got some simple algebra. Z equals x minus mu over sigma. I've got z, I've got mu, I've got sigma. Multiply by 2050, add 67.9, and as it turns out, x equals 64,312. That means I expect 4% to make it to 64,312 and fail. No, that means no more than 4% will make it past 64,312. Some might only last 50,000. Some might last 64,311 miles. But I know that 4% of my tires, if I set my warranty to 64,312, 4% of my tires are going to get replaced. And that's what I can afford. That was starting with this proportion, finding this area, using this area to find the z-score, and then using that z-score in this equation to solve for x. So I can move backwards from the area into the tail to find out exactly what that x value is. Ain't that some special? Similarly, you can use, if you don't want to use the table, there's an Excel function which will allow you to do that. Norm inverse, norm, N-O-R-M-I-N-V, will help you do that. What we've covered now in two parts. The first part was talking about the theoretical, how to get to z a little bit, what the nature of the normal distribution is, platykurtic, leptokurtic, and mesokurtic distributions as they relate to the standard deviation, how peaked the distribution might be. But our big focus today, at least in this little video right now, was talking about how to use this process when you draw the picture, right? The process, draw the picture. Go from raw score to probability or probability to raw score. Now that's some special, I really think. I hope you've learned something. I am done.